what do you do? How do you solve? If you still insist you want to use the pooled OLS, then what do you do? Well, if you want to use the pooled OLS, guys, you can do it, but you have to make corrections for the potential heterescedasticity and autocorrelation, which may be hidden because you use that model. So you're kind of now going to have a new pooled OLS, and you will use a white heterescedastic consistent estimator, the standard error, okay? Because that one is more robust to both serial correlation and heterescedasticity. This white cluster heterescedastic consistent estimator, this thing we've spoken about it. Okay? There are several names for it, and the ones that is well known is the Newey-West standard error. Okay. So you can use that, but this does not solve all the problems of the pooled OLS. Okay. Having said that, let's go and correct that with the model. And to do that, you need to install this package, which is known as library sandwich library LM test. Both of them you have to install and then invoke them. So guys, let's go to the data set. This is our R console. And in this R console, this was the pooled OLS that we ran. You might see it in command number 403. That's the pooled OLS. Now, what we want to do, let me just zoom in slightly. What we want to do is we want to now go into this pooled OLS, which we have already run. And this time, we try and correct it with the HAC. The HAC is the heterescedastic autocorrelated standard error. First, we need to invoke the library command and the LM test. So you do that library, and I know most of you have got the commands already. And then you do the LM. And we are going to do this command to get the standard coefficient. Remember, what it's doing is that it's correcting only the standard error. Only the standard error. Okay, only the standard error. So you run for the coefficient test and look down here in the console, and you will see that in this context, the coefficients that you are seeing there, they are all the same. The coefficient, you can see that. Now look at the standard error. Look at the standard error for experience. Okay. It is 0.136. Okay. Let's go to the original model. Okay. And this is a standard error for experience. Okay. It's the same thing. Okay. It's the same thing. This one gives us the same thing. Because again, we are repeating that before we go and do the HAC. Okay. So let's run the variance covariance matrix, which is the coefficient, the standard error correction. And you use this command, which is known as coef test. You write the name of the model, and then the variance covariance matrix is equal to VCOV HC. Okay, you run that. And this is the result you get down there in the console. Now you check that, and you see that some of the time dummies are no longer significant. Okay. Now look at the experience. The standard errors is gone up. It was 1.3 something. Now it's gone a bit up. You can see that. Now the coefficients are the same. The coefficients will not change, but the standard errors will change because you are correcting for the standard errors. And you can see that here. Everything else will remain as it is except the standard error, which means that you are going to get different p-values. You can see this was original, and this is now the corrected one. And so you can see that some of the coefficients, you know, for example, if you look at this coefficient, the experience square, it was significant at 5%. It was significant at 1%. Well, at 1%, yes. And now it is significant at 5%. It's now significant at 5%. Okay, so it wasn't, if you look at the original one, look at it here, you will see that there are 2 stars. And when there are 2 stars, it means that it's significant at 1%. but with the correction, you can see that it's significant. So it means that it may have inflated the results. Okay. So that is a way to correct for that. Now there's another command you can use to correct for that, and then even indicate certain things. Because the heteroscedastic consistent standard error approach, the variance covariance matrix, okay, what it does is it estimates the variance covariance.
Now that we have corrected.
Is somebody asking a question?
Yes, Doc, we want to see the R square now that
there's no need to see the R square because nothing changes. It's only the standard error that is changing. Please note, it is for the coefficients. The coefficient standard errors. That's what you are correcting. Let me go to Grace. Grace, you have a question.
Yes, Grace. Please, why don't we use the robust Newey-West here?
Oh, you can use it. We are going to use it. You can use it. There are several of these heteroscedastic corrections. Several of them. You choose the one that you are comfortable with. In fact, even there, you have to even indicate which kind of clustering you are doing. If there are a lot of group in your work, the cluster here, I've indicated it with a time clustering. So if you want clustering to be on time, you indicate it. If you want clustering to be on the individuals, you indicate it. And then when it comes to the type of heteroscedasticity, there are about 3 of them here. Arellano bond 1, the white 1, and then the white 2. All of them you can read about them. The white one allows for the general heteroscedasticity, but no serial correlation is corrected. That's a white one. Okay. And then the other ones will have their own. I'm not going to go through the differences in each one of them. You also have to indicate what kind of clustering, whether you are telling the software that there are a lot of group dynamics or there are a lot of time dynamics. You indicate that. If it's time dynamics, you indicate. If it's not time dynamics, you indicate. You can even indicate the type of heteroscedasticity here. You see, at the top here, I've written type 1, HC1. And please check the command instruction. You see HC0, HC1, HC2, HC3, and all of them have got certain things. And the lady just asked me some few minutes ago, now what about using the Newey-West? This is a Newey-West. Okay? So this is a Newey-West standard errors, okay? Which is the one you might be happy and familiar with. So you can use that. I called it calls.nw. It's my own name. And so you can run that. Okay, let's run that. And when you run that, this is what you get. You guys may have realized that Newey-West has consistently been very good chap. Okay. Again, you could see that in this Newey-West, just show you something. In this Newey-West, you will notice, and I like to show you this. You will notice that if you look here at the standard, at the estimates have not changed. Okay, the estimates haven't changed. They are still there as it was before. The estimates are remaining at that place. Now, what is changing here is the standard error. So when you look at this standard error here, that is what is changing. Now, we are not interested in the R squared, the F statistic and all of that. They are going to remain the same as before. Okay. Remember, you are just correcting some portion of your work. It doesn't mean you're solving a big deal of your work. And that is why you later realize that Pooled OLS solves some of the problem and not all of the problem. So the standard errors here have changed. And that standard error, the Newey-West standard error, I told you the last time, is a very, very good correction because it corrects for both heteroscedasticity and autocorrelated standard errors. And that one is showing significance. Just some of the time dummies are still what? Significant. And you can see that by the year 1987, nominal wages have increased significantly. You can see that. So the Newey-West standard errors will correct for some of the problems. And it appears that when you corrected for the standard errors, now you are having what? The significance as you had wanted. Please note that some of them corrected for only heterescedasticity, but this one is correcting for both heterescedasticity and autocorrelation, the Newey-West. And that is how it is got to be. So you can use it and correct it. But again, it doesn't solve all of the problems. Let's not forget that. It doesn't solve all of the problems. So this is a Newey-West standard error. And of course, like I indicated, there are several other things you're going to use to correct for them. But by now, you guys may have realized that the Newey-West standard error stands really good in dealing with both heterescedasticity and autocorrelation or serial correlations. If there are groups, you can specify that cluster. Okay, you can specify that cluster also here inside the Newey-West. Okay, if you believe, let me just go back to the preamble and specify that for you to see. So this is the Newey-West that you have here. Okay, I can just go up there. Just want to show you something. And then the method, I can specify this. I just want to be sure that it works. Sometimes it's not all the time that it works the way you want, because the Newey-West is a very unique one. So I'm going to specify time cluster. And I'm going to specify method Arellano. I just want to see. Like I said, I doubt if it will work, but let's see. Let's see. Okay, it does. So again, that changes some few things. Some things are significant, some things are not significant. It depends on which one you believe is there. It's not a matter of try and error. It depends on which type you are using. And whichever type you are using, given your expectation, we've already discussed this thing. You use that one. Okay. This Arellano bond, you can change it. Okay, and then use a different one. This HC1, all of them are inside. If you go and type it in the help section, it will give you this cluster. You can do cluster for group instead of time. So you can change this group. Okay, if you believe that the clustering is for the group, and there you go. Okay, there you go. You can see that, you know, you have some very beautiful, and in all of them, remember that only the standard errors are changing and not any other thing. Okay. So you just have to know which one you're dealing with. And then if you believe that there is time heterogeneity, group heterogeneity, whatever, that's what you specify. And then you get the result. Okay. So that is the way, one way that corrects some of the problems of OLS. That is one way that corrects some of the problems of OLS. Pooled OLS in particular. Pooled OLS.